In the current pandemic, people are looking for ways to avoid exposure to COVID-19 while still venturing outside. Our product, COVISCAN, is designed to provide these individuals with comprehensive COVID-19 information through graphical data visualizations. This way, they can make informed decisions about venturing outside. In this presentation, a demonstration of a working prototype will be shown, and system architecture design alternatives will be discussed. Finally, it will finish with a short summary of COVISCAN. This is a demo of the COVISCAN web app. When we come to the home page, this is what we see. The Ontario region has been selected, and we are currently looking at Toronto. These areas here, indicated by the red and blue dots, are possible COVID-19 hotspots, which is formulated based off of data collected in the data source. We can move down here to view data visualizations. Currently in this prototype, we only have data for New Brunswick and Ontario, so that is what is being reflected in these pie charts. If we go lower, we can see a geochart where we can select different statistics, such as new positive cases, new deaths, or positive cases, and the map accurately reflects these updates. COVISCAN is built following two architecture designs, three-tier client-server design and model view controller design. The concrete architecture exhibits both styles at the same time, with the client-server style being the predominant architecture. By implementing these design choices, the following benefits are achieved. The client can be lightweight and work via server requests. The business logic is separated from the end user. The system can mix end user platforms like mobile and desktop. The system can be scalable as more supported regions are added. New servers can be added too. The end user client can have many views, potential for adding more views as well. The end user is removed from low-level operations, and future interactions with server data can be improved or modified. Client-server relationship is carried out by the user and their browser acting as the client, and the Firebase-hosted web service acting as the server. It's built in a traditional three-tier structure, with the tiers being the front-end UI, the back-end logic, and the database. Once the user accesses the front-end maintains a client-server interface with the back-end, where it serves logic to view. The server is also responsible for asynchronous business logic, like populating the database, which should be hidden from the user. The MVC style is integrated on top of the client-server setup. The view can be explained as the React-built UI that the user sees and interacts with. This is where the user accesses presented data and chooses what functionality they want from the application. The controller encompasses all input taken from the user by the React UI. The inputs are used to make function and API calls, thus controlling data flow and use. The final model partition entails the entire server side, which is responsible for all the business logic. The server manages data, responses, and requests, and as a result, is the entire model of the system. In finalizing the concrete architecture and starting development, a minor modification was made to the system architecture. This modification is regarding the MVC style. Previously, it was planned to incorporate MVC entirely in the front end or client implementation. As we developed the application, it became clear that our MVC model should not only be in the front end. Since we would like to separate business logic from the user, the model is better suited to the backend. This is merely a notation definition change and doesn't really influence how we implemented the product. It does, however, reinforce our guideline for a lightweight and separate client.
Now I'll be discussing the high-level architecture. COVISCAN is a web app, so all interactions with the system will be made using an internet-connected device through a browser. Any UI interactions that deal with COVID-19 visualizations will send requests to the API. This request provides information necessary for graphing the corresponding visualization. The serializer interacts with the query service to get the appropriate COVID-19 info from the database. The query results are then formatted by the serializer. The formatting is required so that the COVID-19 information is usable by third-party visualizations libraries.
The overall architecture can further be divided into subsystems or components. Each component is a module that performs a set amount of functionality and has an interface to other components. This diagram shows an outline of all the components that make up the system. As you can see here, the components are separated into containers to visually demonstrate how they actually make up the chosen model view controller and client-server architecture. The model is made up of all the business logic and persistence. This is the actual application functionality and is also considered the server. The view is the front-end user interface with its API interactions as the controller partition. Those two together are considered the client in the client-server architecture.
COVISCAN makes use of the power of React.js and Material UI for its front-end design and state management. On visiting the application, the user is greeted with a map overlaid with hotspots to indicate areas with active COVID-19 cases. This map uses Google Maps API for rendering the interactive map and the heat map. On scrolling down, the user is greeted with pie chart graphs and other visualization elements. These make use of Google Charts API to plot the data. The data in question is pulled from our backend storage through RESTful calls to internal endpoints and is asynchronously piped to each visualization element to be rendered. We chose React for its ease of use, extensive library support, and the swappable plug-and-play nature of the internal components. For storage, COVISCAN makes use of Firebase Firestore for its data storage. Firestore is a NoSQL document-oriented database that is horizontally scalable in nature and fits COVISCAN's large data storage requirements. All database interactions are performed solely through the backend function calls, where database rules enforce the schema. Here you can see a screenshot of some of the fields within our document storage. The APIs used by COVISCAN are Google Maps and Google Charts. These are third-party services which are leveraged in our application to provide functionality our team would not have been able to build from scratch given the project's time constraints. These APIs allow the UI to embed the aforementioned map and charts for data visualization. The interface between the front end and the APIs are done through HTTP requests. Backend functionality in COVISCAN is also hosted on Firebase, the platform as a service used in this project. Firebase functions and Express.js are used to host a serverless API where COVISCAN's visualization endpoint reside. These endpoints are interacted with through RESTful HTTP GET requests. In order to provide the front-end visualization with usable data, the backend utilizes serializer and query services. Firstly, the Firestore query is processed by the query service, where the raw JSON response is collected. Then the serializer service is leveraged to normalize the JSON response into a 2D array, which is usable by the Google Charts API. COVISCAN in its current release does not implement concurrency, as most operations are simply read requests that happen asynchronously. Firebase, however, handles concurrency in typical CRUD operations. For example, if a transaction reads a document and another client modifies any of those documents, Cloud Firestore will retry the transaction, ensuring that the transaction runs on up-to-date and consistent data.
With everything mentioned about the subsystems in mind, here's an example of what happens in the system when a user accesses the web application in order to view analytics data. At first, a landing page is displayed with default initial maps and charts. When a user selects a new province, the view updates the charts. This is done by a web client request to the visualization API in the backend. The API gets the data from the Firestore and returns the COVID information necessary to update the charts. As you can see, this sequence goes through all three layers of the web application.
Our design choices are a result of use cases, quality attributes, architecture, development operations, and third-party services. Our first prototype focuses on two use cases, the first being the user selecting a map region, indicated as the use cases in the top of the diagram, and the second use case is the user viewing the data. Use cases were helpful to understand how the major actors of our application interact and which actors would be called upon for our prototype. When we designed our application, we considered the benefits and trade-offs of each addition we made to our project. A quality attributes table was created, and here are just a few examples to demonstrate why this approach was useful. By letting our quality attributes inform our design decisions, we were able to justify the use of Firebase for our backend, React.js for our frontend, and various APIs to satisfy the performance, security, privacy, usability, reliability, availability, and scalability of our application. Our web service is hosted entirely on Google's Firebase. As a result, the entire system is hosted on the cloud. and enjoys all the benefits of accessibility, scalability, and reliability. Since Firebase provides simple interaction between front-end, back-end, and storage, it also reduces development time and learning curve. Another new technology for some team members was service-oriented architecture. COVISCAN is developed using many web services, such as Firebase, and all the APIs required for maps and data visualizations, in addition to the Firestore web storage.
Now we'll be discussing alternatives. For our alternative architectures, we considered repository and publish subscribe. While repository style is efficient at storing big data and is easy to manage, COVISCAN has no need for complex data computation, long-term storage, or saving a system state. COVISCAN revolves mainly around requests for specific regions. This is where we considered publish subscribe. The main consideration was that the client doesn't request data at a fixed period, it needs it upon request and needs to be served at that time. For cloud service alternatives, we considered AWS and IBM Cloud. We ended up going with Firebase. Some members of our team were familiar with Firebase, so this decreased any overhead in development. Following the KISS design principle, by keeping things simple, we were able to avoid unnecessary complications throughout SDLC. Web apps can be deployed to Firebase extremely quickly. This gives a lot of time back to the dev team to focus on maximizing the user value of COVISCAN. In conclusion, the client-server and MVC architectures manifested most naturally for COVISCAN. The web app runs on the Fern stack, that is, Firebase, Express, React, and Node. Due to the schedule constraints of school, ByteMe adopted a hybrid form of Agile. We look forward to improving our process as we go through our next sprint and providing maximum value to our customers.